This is the second of two papers on the low resolution spectroscopy of Mira's uh, with myself and John Martin. So this is where we're going to go in the course of the talk. There'll be a very brief introduction, a fairly brief discussion of the observing equipment and target stars. And I want to spend most of the time on the results X and R octans and R Centauri. After that, I will wrap up. So to the introduction, this work was started about 2015. There has been a previous paper presented at the symposium in 2016, and there's also been two journal articles, both in the Journal of the American Association of Variable Star Observers, and the details are there on the screen for you. There's also a third paper on the work on R Centauri, which is now being written up, and we hope to publish that later this year. Mira's systematic variation in brightness is caused by pulsation, and this has two effects on the star. It changes both the diameter of the star and also its effective temperature. For a star to be classified as a Mira, it must have a light curve amplitude in the visual of a minimum of 2.5 magnitudes, but they can be as large as 10 magnitudes. So these are very large changes in the brightness of the star. In terms of temperature changes, they can have changes up to 500 degrees Kelvin. And it is these large changes which allow us to use low resolution spectroscopy to do useful science on them. Usually, if you want to determine the spectral type of a star, you take the spectra of the star of interest. Then you also take spectra of a number of known standards, and you compare the two, or multiple comparisons, and this is known as differential spectroscopy. The problem with working with red giants such as Mira's is that all red giants are variable to some degree, and hence there's no true standards to work with, and this creates a problem which we have to resolve. So that's all I want to say by way of introduction onto the observing equipment and stars. In an era of multi-million and sometimes multi-billion-dollar instruments to do science, it is a question for amateurs that often comes up is what can I do on a very limited budget? So what I have is an Explore Scientific 80mm refractor, and that's quite a small telescope as far as telescopes go. The mount I have is Celestron's entry-level mount. The CCD camera that I have was not ATIC's entry-level one, certainly just one step up, but a very modest camera all the same. And finally, the Peyton Hawksley Star Analyzer 100 was less than $200. So on a fairly limited budget, I hope to convince you that you can do useful science with something like this. We also use the AAVSO-NET Bright Star Monitor telescopes in Australia, of which there are two, but primarily we use the BSM South, which at that time was a 72mm refractor, again, small telescope to do B and V photometry. In terms of resolution, these grating spectroscopes typically have R values between 50 and 200. This is really down the low end of things. So the choice of R Centauri came from Matt Templeton's original research proposal on long period Miras, and he defined long period as those with periods exceeding 450 days. We observed R Centauri for a full cycle, and then once we had done that, we realized there were a number of problems that we needed to solve to get useful science from the observing that we were doing. And that's when we started to look at X and R octans to try to solve a particular problem of when the star crosses about M6, maybe a little later, at which point vanadium oxide starts to form in the atmosphere, and that depresses a key continuum point. An advantage for Southern Hemisphere observers like myself is that all major observatories are sufficiently far north that observing near the pole is actually quite problematic for them. It's too low in the sky. So it creates an opportunity for amateurs to observe deep in the Southern Hemisphere and do some useful science there. Another advantage is that particular area of the sky, the South Celestial Pole, is relatively barren with few stars bright enough to be seen by the naked eye. and this helps to reduce the problem of contamination of a spectra by a field star when not using masking, which I was not. So here's the details of our stars. So here's our 3 Miras here. They are all M-type Miras, and you can see the published range of their spectral types. So M3 to 6. A key one here, our Centauri had a published range of M4 through to about 8 M8. I won't say much about these at all. These are our comparison stars, but here's the key problem is that to a greater or lesser extent, they're all variable to some degree, and hence there's no real true standards to work with when doing differential spectroscopy. So on to the results. X-octans is our M3 to M6 Mira with period about 200 days. So here's a couple of spectra from them. This one here, this blue one here, this is from up near maximum light. And then the black one here is towards minimum light. And just looking at these, you can see substantial differences and substantial changes in the spectra from maximum to minimum. So look in the key region here of 400 to 600 nanometers, quite a bit of light being produced by X-octans towards maximum, but substantially less towards the minimum. These points here, 1, 2, 3, 4, 5, these are what we call our continuum points, C1, C2, C3, C4, C5. If you look at the heights of them there at minimum, they're quite distinctly different, although definitely different at the maximum. The differences are nowhere near as much. Other key thing here, this is the key titanium oxide line, which is absorption line, which is used what we both call the wing ratio, which measures against this peak here, and a ZZ ratio, which measures against that peak there. And you can see that those ratios are going to change dramatically as this star cycles through this. Down in the deeper part of the infrared, there's very little evidence at maximum of the C4 and C5 points, but they're quite distinct points here towards minimum light. So this graph here presents the light curve. So here's the light curve of X-octans while we're observing it, including both visual and V-band photometric observations. And then up here we have, in the blue, we have what we call the ZZ ratio. That's the titanium oxide line at 719 nanometers measured against a continuum point at 702. And then this red one is what we call the wing ratio, which is the same titanium oxide light point against the 754, 756 nanometer continuum point. And in this star, the wing ratio definitely does a better job. And there's even subtle differences that get picked up. So if you look at this minimum here, it's a bit lower than that minimum there. And that's reflected in these ratios here. And similarly, this minimum here is a bit higher than that one, and that's reflected in those minimums there. Now, the thing is, you can't take a light curve like this and turn that into a spectral type, but with appropriate calibration, you can take these wing ratios here and turn them into spectral types. And we were basically able to confirm that it does range between about M3 and M6 as in agreement with the published literature. Moving to R octans now, this is our much cooler Mira, also longer period Mira. So here's a light curve, just some historical data from the AAVSO database. And you can see, in common with many Miras, there are times when the maximums are quite bright compared to other times when they're relatively dim. And similarly, if you go to the minimums, there are times when you have very deep minimums and other times when you have shallow minimums. Now, it just so happened that when we were observing it, it was in a time when it had low maximums and deep minimums. So it was cooler than its historical average, although definitely not outside its historical range. So here's 3 spectra from R octans. So this is again up near maximum light here, this bottom one, then about mid light through here, and down minimum light here, which is actually quite a noisy spectra because it was very dim when I was observing it. So again, changes here in the 400 to 600 nanometer range, and reasonable amount of light coming out there at maximum, decreasing towards midlight, and almost nothing in that range down at minimum. Looking at our continuum points, here's C1, C2, C3, C4, C5. The C3 point here has a problem, and this little notch that you see here at maximum light is the vanadium oxide molecule, which is forming in the atmosphere, and it's depressing that continuum point. As you go cooler, it becomes a definite little absorption line here at mid-light, and down at minimum light, there's a definite absorption line associated with that vanadium oxide molecule, which is the thing that makes it problematic for using in the wing ratio. Other thing you see is like here at maximum light, the C3 point is the peak, the highest point, but here's C4 a bit lower, and C5 is way down here. If you go to midnight, the C3 point is lower than the C4 point, and also the C5 points come up. So where the energy is being output is shifting deeper into the infrared. So that when you get down to minimum light, again, this is quite significantly lower than the C4 point, and the C5 point's almost the same height now as the C3 point. So the energy is shifted deeper into the infrared. So here's some continuum ratios. These are what we consider to be the two best, although the top one, the C1 against C3, certainly has a problem once you get down to magnitude 10, 10 and a half or so. But above that, it does seem to be doing quite a good job. So here's your light curve there. And this again has both visual and V-band photometric data in it. But this was a good one down here. This is the C2 against the C5 ratio. And you can see quite distinct peaks, long periods down here quite low. And there's even differences, like this peak here had a maximum magnitude about 8.3. That one was about 7.7. And of course, the ratio reflects that here. And also the shape of the peak, again, is reflected in these ratios. And as I said before, you cannot take a light curve and turn that into a spectral type, but with calibration, you can take these ratios here and turn them into spectral type. And we certainly thought that our octans was going nowhere near M5, probably was not even coming up above M6 when we were observing it, and maybe going as late as possibly M9. So onto R Centauri. R Centauri is the prototype of the dual maximum Mira variables, and I'll show you a light curve of that fairly soon. They exhibit double maximum with alternating deep and shallow minima. But R Centauri has evolved rapidly in recent years, and in the most recent cycles, what was that second maximum is no more than a small rise on its descending part of its light curve. And also the light curve itself has reduced in amplitude from 4 to 6 magnitudes, and its period has dramatically changed. The reason for this, it's thought to be undergoing a helium shell flash. So that's when inert helium in the star ignites and begins to burn in a thermonuclear sense, injecting an enormous amount of heat deep into the star, which lets then work its way to the surface. Now, potentially, this could result in a dredge-up event, bringing particularly carbon into the atmosphere, which could change its spectral type. So here's a light curve. So you can see here these two dual maximums. They're approximately the same brightness, but alternating shallow, deep minima. So this was when it was clearly a dual maximum Mira. This data here comes from just before we started observing it. And you can see that it has a single maximum now, and what was a second minimum is often no more than a small rise. The other thing that's noticeable is instead of running down to maybe magnitude 12 or lower, it was rarely going below magnitude 10. So it's significantly brighter in the bottom part of its light curve. So here's 3 spectra. At the bottom one is an M-type Mira, and that is actually, in fact, it's R Centauri itself. And that spectra is dominated by the titanium oxide absorption lines. You can see them here in the spectra. If you put more carbon into the atmosphere, such that there's approximately similar amounts of carbon and oxygen, you get an S-type Mira. And this is TT Centauri, which is one. It's fairly noisy spectra because it was quite dim when I was observing it. but you can see that the structure of the spectra is quite different from the M-type. Putting even more carbon into the atmosphere will give you a C-type, and BH crucis was a C-type, and you can see that the absorption lines are molecules involving carbon. This is carbon, carbon 2, and then these are CN lines here. So if there was a dredge-up event and carbon was brought up into the atmosphere of R Centauri, and it did change its spectral type, you could see it without any particularly sophisticated analysis of the spectra. So here's the wing ratio, which for this particular star was quite good. So here's our light curve down here from the time we are observing it, including both visual and V-band data. And then this is our wing ratio here. Now, this is the early period when we were sort of just trying to figure out how to do this, and this may not be particularly reliable, but once you get past here, it becomes quite good, except for maybe a point there and a point there, which might have had some problems. Now you can see it come rising up over there, matching that light curve quite well. And again, you can take these ratios and you can turn them into spectral type. And we certainly believe that currently R Centauri does not go much later than M6, certainly goes nowhere near M8, supporting the hypothesis that a helium shell flash is in progress, and potentially there may be a dredge-up event, but we didn't observe one. So these are the continuum ratios here. This is ones involving C1 against C2, 3, 4, and 5. A thing that's quite surprising about them is that they were quite flat across the period when these, there's definitely changes in the light curve, but not much changes in these ratio here. The only real change we got in these ratios when it came up to its major maximum here. And over here, again, these were relatively flat. Going to the ones with C2 against C3, 4, and 5, that's these ones here. Again, very flat across this period here, and only a real rise when you get to that period there. So this is C3 against 4 and 5. Again, very flat in here, a rise over that period there when we come to the maximum, and C4 against C5, and that's very flat. So in this particular star, it looks like the wing ratios are the ones to use. So to wrap up, we think that we've addressed the most pressing issues in getting useful science from low resolution spectra for M-type Miras with spectral classifications of M3 and later. Using the wing ratio for M3 to M6, perhaps a bit later than that, looks very reliable. Once you definitely get beyond M6, switching to or adding these continuum ratios certainly is quite reliable, and that should allow you as an observer to get quantitative data from the very cool parts of Mira's cycle from these low resolution spectra. Now, each system needs to be calibrated against known standards. That's a bit problematic, but it can be done. So overall, we think these methods are ready for prime time, which means that if you are observing M-type Miras in your observing program, you can usefully add low resolution spectroscopy to a photometric observing program. A couple of things we haven't done. We haven't looked at Miras with spectral types earlier than M3, and we've done very little, if anything at all, on the C and S type Miras. So to the questions, comments, and helpful suggestions.